So in the first part of this, which is the second lecture, we saw that by solving Schrödinger's equation, we can determine the wave function and the corresponding energy values or energy levels that the electrons can assume in any given atom, but for example in a hydrogen atom. So we got discrete or quantized energy level. So how do the electrons distribute themselves among these different energy levels? So the electrons tend to occupy the lowest energy level which are available for them. So in the hydrogen atom, this would correspond to the ground state, which is this one right here, the one with the lowest energy. So at a temperature of 0 Kelvin, the electron would occupy the lowest level available. If you supply energy to a given electron, it could temporarily occupy an excited state. For this to occur, the energy that you supply to the electron cannot be any energy value. So the energy needs to be equal to the energy difference between the current electron level or the current electron energy. So for the hydrogen atom, which only has one electron, this would correspond to n equal 1, and the next level available with a larger energy. So if we look at this, you would need to supply enough energy in order for the electron which has this amount of energy to rise up to this energy level. So it is only logical that you would need to supply an energy that is of equal or larger amount to the difference between this energy and this lower energy right here. This energy given to the electron can be supplied by different forms. So it could be energy given as heat, or thermal energy, electromagnetic radiation. So for example, if you impinge light into the atom, it could perhaps absorb light. An electron could rise from the ground state up to an excited level, or an electrostatic field, etc. Now let's suppose that the electron is temporarily in an excited state. So in hydrogen, let's suppose that the only electron, instead of being in the ground state, was up here due to the supply of energy in any given form. It would possibly stay in this excited state for a temporary or a limited amount of time. So eventually it would return to the ground state. And in doing so, it would need to release this energy back to the system or to the environment. So energy conservation always takes place. When the electron returns to the lowest level available to it, it gives back that energy, and this energy could be given off as light that is emitted by spontaneous or stimulated emission. Okay, so the energy of the light emitted would be exactly the energy difference between the two levels, or it could be given off as heat, thermal energy, which would become vibration in the atoms of the lattice of the solid, and so on. Okay. Also notice that the energy levels can be occupied by more than one electron. So electrons with different spin angular momentum or orbital angular momentum can have the same energy and therefore occupy the same energy level. So what we've seen so far are the wave functions and energy values of isolated atoms. But this raises the question, what would happen if we were to consider a solid, okay? So let's see, the radius of most atoms is around 1 angstrom. 1 angstrom is 0.1 nanometers. If you take a guess, in the gas state, the typical distance between atoms or molecules of the gas is anywhere from 10 nanometers to 1 micrometer. Okay, so this is 100 to 10,000 times the radius of the atom. So the distance between atoms is 100 times larger than or more than the radius of the atom. At these distances, the electrons in any given atom or molecule do not feel the influence of the electric fields of the other atoms' nuclei. So it's like one atom will not perceive the other atoms because they're so far apart that they effectively do not feel the electrostatic forces of the other atoms, nuclei, and so on. Okay? So in that case, the energy levels and probability density functions of each electron are not disturbed by the electrostatic forces of the adjacent or the neighboring atoms. And the energy levels and the wave functions are going to be the same as those of an atom which is isolated from any other atom. Okay, so this is how a gas would behave. Okay, so this leads us to the discussion of how the band structures, the band diagrams are originated in a solid. Okay, so in the solid state of matter, the typical distance between atoms or molecules is much smaller. So take a silicon crystal lattice, for example. We just saw that the lattice constant is about half a nanometer. Okay, so this is 5 angstroms. Well, this is much closer to the radius of the atom, which is around 1 angstrom. Okay, 5 angstroms is much closer to 1 angstrom than, say, 10 nanometers is to 1 angstrom. So therefore, the atoms start perceiving each other. They start feeling the electric fields of the adjacent atoms. So since this distance is much closer to the atomic radius, the electrons in one atom can feel the electric field of the nearby atom's nuclei. And what this does is that it causes the discrete energy levels of the isolated atoms to split, forming multiple energy levels. So if you have one isolated atom, it has discrete or quantized energy levels. When you bring these atoms together, the individual energy levels of the different atoms are going to split. Of course, this is sort of a phenomenological explanation, but this is what actually happens. And if you solve Schrodinger's equation for the electron wave function subjected to the influence of a whole lattice of atoms instead of a single atom, you will find this energy level splitting in a more rigorous and mathematical manner. Rigorously, this is found by solving by any technique Schrodinger equation considering the potential of all of the atoms in the solid. Okay, so let's try to use illustrations to get a better grasp of this concept. So what we said is that if you have an isolated atom, it's going to have discrete quantized energy levels. In a gas, okay, the atoms are so far apart that this atom does not feel the influence of the electrostatic potential of the nucleus. So these electrons are not going to feel at all attracted to the nucleus of this other atom, which is so far away that doesn't happen. So the energy levels are going to be the same as if this atom was completely isolated from the universe, okay, because the atoms are so far apart. Now let's say that you were able to bring this other atom close to this one here, right, to a distance which is comparable to the radius. Well, what would happen then is that these levels, the individual levels, would split. Because the electrons from Pauli's exclusion principle, the electrons cannot have the same absolute energy, so these different energy levels would split. So you have, for each original energy level, right, you would have one slightly below and one slightly above, okay? And this would happen for all the energy levels. Now, what if we extrapolate and bring even more atoms to this mixture, okay? So if you have in this case, what would be a one-dimensional lattice, okay, 1D crystal structure, for every additional atom, you would have additional splitting of the energy level. So you'd have many discrete energy levels. Now, if you go further and consider a three-dimensional lattice with as many as 10 to the 23rd or 22nd atoms per cubic centimeter, you would see that this level splitting would lead to an enormous amount of levels originated from a single level. So you would have many. In fact, this is the reason why we have calculated the density of electrons per cubic centimeter in the beginning of this lecture, because this will give us an idea of the order of magnitude of how many levels you would have per original energy level in a solid, okay? So in this process of splitting of levels, since the new levels have originated from the original energy levels that the electron could assume, the originated levels are going to be allowed energy levels, which will be actually energy bands. They will almost, and the emphasis on the word almost here, almost form a continuum of levels, okay? It's in reality, it's still discrete levels, but they are so close together that it's almost as if you had a continuum of energy levels effectively forming an energy band. So this is what energy bands are. And depending on the distance between the original levels, there might come about an interval of energies here which cannot be accessed by the electrons. So in this process of splitting, say that the splitting leads to this band right here and this band down here. If they are far apart enough, there might be a region here that does not have energy levels at all. So this interval is going to be the band gap. The forbidden energy values, right, are going to be in this region. Okay, so that's how the band gaps and the bands, the energy bands, come about. Okay, so you have intervals here where the electrons, intervals here for which the energies cannot be accessed by the electrons. So to summarize, the energy levels become bands due to the fact that you have brought many atoms together, and the energy levels splitting is going to be so much that the original energy level is going to become a whole band of an almost continuum of energy levels. And therefore the electron is allowed to occupy states within the allowed energy bands, but the electron will never assume energy values within the forbidden bands or the band gap. Also, the energy difference between the highest occupied band, which is called the valence band, and the next unoccupied band is called the band gap. Okay, so going back to the figure, these are the forbidden energy values which are unavailable to the electrons, but the difference between the lowest energy value of this band and the highest energy value of this lower band is the actual band gap, which is going to be a quantity given in electron volts, which is a unit of energy. Okay, so the actual energy difference here is usually called the band gap. We also saw that each of the energy bands is almost, but not quite, a continuum of allowed states. So they're still discrete states, but they're very close together, that they almost form a continuum. Within each band, there is as many discrete energy states as there are atoms in the solid. So this gives us an estimate of how many levels per band, which is 10 to the 23rd, 10 to the 24th levels, whole lot of levels per band, which is what is stated here. This turns out to be of the order of 10 to the 23rd allowed levels per band. Okay, so just before we finish, just to recap the concept of valence band and conduction band, as we saw, the electrons are going to fill these energy bands from the lowest to the highest energy. Okay, the electron will always tend to occupy the states associated with the lower energy levels first, and therefore you are going to have an amount of energy bands which are completely filled right here, and then it's going to come to a point where the next one over might be empty. So when this happens, the highest energy band, which is completely filled, is the valence band, and the lowest energy band, which is completely empty, is the conduction band. Okay, so this is essential for the operation of semiconductor devices because only electrons which are in the conduction band are able to move freely inside the solid. Electrons which are in the valence band remain attached to the atoms. All right. Okay, so what we saw in this lecture was the concept of crystal structure and how the band diagram in a solid originates from the discrete energy levels that we have in isolated atoms. So thanks very much for your attention, and I'll see you around.